Okay, so let's continue. There seems to be some problem. I cannot record for more than 10 minutes for some reason. Um, so, as we were discussing, that's the blue area, that's the fin. Delta x is the length of the fin, t is the thickness of the fin, p is the parameter of the fin, a is the area, cross sectional area of the fin designated by AC. The base temperature is TB, that's the place where you find the base temperature. This is the place of temperature, base temperature. T infinity is the surrounding temperature, and LC is the corrected length. One of the important aspects to understand is this corrected length, right? Uh, Before we do that, let me show you something. So let me go back to my notes here. So why do we have this corrected fin length? What's the meaning and purpose of corrected fin length? Okay, so let me explain you this. So let me take this. Yes. So let's say you have a fin whose length is L and you have some other fin whose length is LC. Okay. As the length becomes longer and longer, the fin turns out to be an adiabatic fin. But both fins give out the same rate of heat transfer, right? Even if you increase the length, assuming that all other parameters are constant, okay, like they're not changing, the adiabatic fin and the normal fin turns out to give the same rate of heat transfer, right? So if the fin is made larger, it makes no difference, right? So hence, in case of rectangular fins, we use corrected lengths. Also, in case of cylindrical fins or circular fins, we use corrected lengths. And the corrected length for rectangular profile is length plus thickness by 2. Now, these corrected lengths uh, help us to calculate, this formula helps us in calculating the corrected length of the fin. The idea behind this is that if you look at both the fins where convection is taking place, the longer the fin, it becomes more adiabatic in nature, right? But the rate of heat transfer remains the same in both the cases, right? So hence we need to use a corrected length, that is L plus thickness by 2 for rectangular profiles. Also, you will notice three A's in the formula. AP means profile area, AC means the cross section area, AF means the fin area that touches the fluid, okay, so to say. So remember this three A's and the corrected length. Okay, so let's go back to our slide. Let's go back to our slide. So that's the purpose of corrected length. So corrected length in case of rectangular fin is L plus thickness by 2. Okay. This is a general formula for long fin. H stands for conductivity, P stands for perimeter, H stands for convection heat transfer coefficient. Pardon me, this is convection heat transfer coefficient, right? This is convection. K stands for conduction heat transfer, thermal conductivity, right? Thermal conductivity. P is the perimeter. AC is the cross-sectional area of the fin. TB is the base temperature. T infinity is the surrounding temperature. In case of extended surfaces, we have 4 cases or 4 types of boundary. Either we may have long fin, right? Long fin whose length is quite large. We might have short fin with insulated tip. We might have short fin without insulated tip. And in the question itself, there might be a specified end temperature. We know the temperature at the end of the fin. So we have 4 cases. Case 1, case 2, case 3, and case 4. All in all, we are concerned about temperature distribution, heat transfer rate, and the efficiency of the fin. These are the set of formulae that we are going to follow when solving the problem. But the question here is, which formula should we use while solving the problems? Or which case should we consider while solving the problem? So let me sort of introduce you to some case studies so that we can find out which formula is to be used when solving these problems. Before we proceed, you may also refer to this formula sheet on the Moodle. The formula sheet is available on the Moodle, and you can use this formula sheet. You can download this formula sheet from Moodle. Now look, let us see the first case study. That is problem number 1. Now consider a very long rectangular fin. Now the question itself says that it's a long rectangular fin. Now if you go back to the formula sheet, which is here, and zoom in. So long fin, the temperature distribution is given by this formula, e to the power minus mx. Heat transfer rate is given by this formula, and fin efficiency is given by this formula. Right. Now, with the help of case study, let me make you understand what are these parameters. You see here in the formula, you can see some new terms like M and L, etc. So let me explain you that. Let me lay out blank. Okay. So you see, the given data says it's a very long it's a very long fin. Okay, it's a very long rectangular fin attached to a flat surface. The temperature at the end of the fin is essentially that of the surrounding air, that is 20 degrees. Its width is 5 centimeter, thickness is 1 mm, thermal conductivity is 200, base plate temperature is 40, heat transfer coefficient is 20, and we need to estimate the temperature at a distance of 5 centimeter from the base plate, and we need to estimate the rate of heat lost from the fin. Now that's the figure. So you can see the length, the thickness of the fin is 1 mm, so that's 1 mm here, right? The base plate temperature is 40, so the temperature here is 40 degrees. The temperature at the end of the fin, he says, is that of the surrounding temperature, so T infinity is 20 degree. T infinity is 20 to 0. Oh. So let me write it here. T infinity is 20. Right. The length of the fin is also given, I suppose. The width of the fin is 5 centimeters. Okay. So we have the width here 5 centimeters. The heat transfer coefficient, so K is essentially given 20 watt per meter square Kelvin, and H is also given 200 watt per meter Kelvin. Right. So what we are going to do is, we know that there are 4 cases in this particular extended surfaces concept. Out of those 4 cases, we need to judge which formula is essentially we need to apply. And in this particular case, we are going to choose formula number 1. And why is it so? Because the question says that it is a long fin. It is a long fin. So we need to choose formula number 1. Okay. So if you see the formula 1, let me write down. The first question that he's asking is, estimate the fin temperature at a distance of 5 centimeters. So fin temperature at a distance x equal to 5 centimeters. This is nothing but 0.05 meter. Now, if you see case number 1, the first column, the second column, gives you temperature distribution. So we have temperature distribution. The formula is given as follows: T minus T infinity divided by T base by T infinity equal to e power minus m times x. Right. So this m is a constant, and this m is given by the formula root of h times p, that's the perimeter, divided by k times a. It's a constant, right? That's the a, area of the fin, and that's p, perimeter of the fin, right? Now, in this particular case, if I see the perimeter of the fin is 2 times breadth of the fin plus thickness of the fin, that is 2 times 0.05 plus 0.001. So this gives me the perimeter 0.102 meter. And the area of the fin is again breadth times thickness, that is 0.05 times thickness 0.00001. So this should give me, let me write it clearly. Okay, so let me write it clearly. So the area is equal to 0.05 times 0.001. So this gives me area of the fin at about 5 into 10 power minus 5 meter square. So I know the area, I know the perimeter. Step 1 is to calculate the value of m. Step 2 is to calculate the value of t, because I know T infinity, I know T base, I know T infinity, I know the value of m, I know x, that is 5 centimeter. So if you plug in all the numbers, you're going to get a T value of somewhere about 29.79 degrees centigrade. That's how we calculate T. Right. To put it in order,